Okay, we're going to work on these 4 problems which you'll find at the bottom of the page with the rules of exponents on it. And you might want to pause this video and try these problems yourself and then look at the solutions and see how they compare. We'll start on the first one. I've cut the page in half so we can refer to the rules of exponents as we go. So I want to calculate x cubed times x squared plus x to the 4 times x to the 1. So all of our rules so far apply to integer exponents, positive or negative or 0, and we can apply the rules here because we just have integers. But we want to simplify this expression, so we want to tidy it up if we can. And we're first going to use the first rule, which says a to the m. So we can use rule 1 here. It says we add the powers when we have the same base, and we multiply. So we have x to the 3 times x to the 2 should be x to the 3 plus 2. This is by rule 1. Plus x to the 4 times x to the 1 should be x to the 4 plus 1. And now that's equal to x to the 5 plus x to the 5. And it's natural to write that as 2 times x to the 5. Okay, that one was pretty easy to get started. The next one is x to the 3 squared times x to the 4 over x to the 5. And we're going to start with that x to the 3 squared, and we have to figure out what the rule says there. For that we're going to use rule number 3 here, which says a to the m to the power of n is a to the m times n. So I must multiply the exponents here, and I get x to the 3 times 2 times x to the 4 over x to the 5. And if you look in your notes, that's rule number 3 I'm applying. So that's x to the 6 times x to the 4 over x to the 5. And now we apply rule 1 again and add the exponents here. So that's x to the 6 plus 4 over x to the 5. And that's equal to x to the 10 over x to the 5. And now, most likely you've done these calculations before and you realize that it's just cancellation, but to be pedantic, we're going to apply rule number 2 here. A to the m over a to the n is a to the m minus n. So I'm going to subtract the exponents here using rule 2, or you might just see this as cancellation. So it's x to the 10 minus 5, and that's equal to x to the 5. So using all of our rules here, we get that this complicated looking thing boils down to x to the 5. Now, this next problem involves a number of variables, so that's our next step of generalization. And we have xy over z to the 3 times x squared times z squared over z times y. So now we're going to change the base, and our bases, we have a number of bases here, and eventually we will change the base to be a function of x, and we'll also change the exponents to be functions of x or functions of many variables. So the calculations get more complicated, and it's important to keep the rules in mind. Okay, first of all, I'm going to distribute this power. A over b to the n is a to the n over b to the n. So I'm going to use rule number 5 here and distribute the power for this first quotient. So that's xy to the 3 over z to the 3 times x squared z squared over z times y. Now again, I can distribute this power over the product of the bases, and that would be rule number 4. So this first one was rule 5 for your reference, and the next one I'm going to use is rule 4, and that says that it's x cubed times y cubed over z cubed times x squared z squared over z times y. Now I'm going to subtract exponents where I can. First I'm going to amalgamate the powers, and I'm going to put all of the x's together, so that's x cubed times x squared times y cubed times z squared over z cubed times z times y. And now we're back to using rule number 1 here to amalgamate these powers. So by rule number 1, I get that this is x to the 3 plus 2 times y cubed times z squared over z to the 3 plus 1 times y, and that's equal to x to the 5 times y cubed times z squared over z to the 4 times y. Now we can cancel or subtract powers of similar variables. So we have x to the 5 times y cubed over y times z squared over z to the 4. And now using our rule where you divide, rule number 2, which says if I divide powers of the same base, then I subtract the exponents. So this is x to the 5 times y to the 3 minus 1, and again you might write this simply as calculation or cancellation times z to the 2 minus 4, and this is equal to x to the 5 times y squared times z to the minus 2 r. It's x to the 5 times y squared over z squared. And that's my final answer, and it is a little tidier than the original fraction I was given. Okay, and lastly, we're going to figure out this one, which again has many variables. And many exponents. So, first of all, by definition, we could use rule number 6 here, but I like to remember as few rules as possible. So, by definition, this is 1 over y over z cubed, and that's x squared times z squared over z times y. And now I can distribute this cube over the numerator and denominator using rule number 5 here. We have a over b to the n is a to the n over b to the n. So y over z to the 3 is y cubed over z cubed. And that's times x squared, z squared over z times y. Now by the rules of fractions, I invert this fraction and I get z cubed over y cubed times x squared and z squared times z times y. Now you might like to just cancel a few things here, or you might just want to put things together. Either way is fine. We have z cubed times z squared times x squared over y cubed times y times z, and that's equal to, amalgamating these powers according to rule 1, z to the 3 plus 2 times x squared over y to the 3 plus 1 times z, and that's z to the 5 times x squared over y to the 4 times z. Now this z will cancel with one of those, or if you like to say which rule you're using, you can say according to rule number 2 here, a to the m over a to the n is equal to a to the m minus n. We have z to the 5 over z is z to the power of 5 minus 1 times x squared over y to the 4. So that's z to the 4 times x squared over y to the 4. And that's about as simple as we can make this thing. And it certainly does look a lot simpler than the initial version. So we'll stop right there.